This right here is called a radical. A radical has two parts to it. We have the power and the radical signed. This is the actually what the radical is. And then it has this radicand, or the argument of the radical, the thing that the radical is acting upon. So these two parts tell us how to use the radical and what we can do with it. Now in this video, we're going to be looking at simplifying radicals and radical expressions. Before we do that, let's look at a couple properties of radicals that are going to help us simplify them. First off, if we have a radical with some power over two things that are multiplying, we can break this up into the radical of the first times the radical of the second. And in fact, this expands on to however many you're multiplying on the inside. It breaks up over every single bit of it. Likewise, if we have a radical over two things dividing, we're going to break this up over the top and the bottom. They're pretty much the same property. That's because they're multiplication and division, which are nearly the same operation. Now, splitting this up, let's look at the square root of 36. Now, the square root of 36, first off, it's you do not see a power on the radical. That's because the square root is used so commonly in mathematics that we've decided to drop the two because it just creates less writing because it's used so frequently. There is a 2 there, however, it's just understood to be there. A radical asks the question, what number times itself the radical power number of times, in this case 2 times, equals 36. And this is 6 times 6. 6 times 6 equals 36. So the square root of 36 is 6. Now we can think of this as a different way using the properties above. 36 is the same thing as 9 times 4. And 9 times 4, we can break up the radical over the two parts using that first rule there. The square root of 9 is what times what equals 9. It's going to be 3 times 3. And the square root of 4 is 2. 3 times 2 is 6. And of course, we get the same answer for both problems. All right, let's look at another one. Let's look at the square root of 64 over 36. We can break this up over each. And if you don't know these things, you can break it down like I did in this portion here. But both of these do actually have answers. The square root of 64 is 8. 8 times 8 is 64. And the square root of 36 we just found is 6. This, of course, can be reduced by 2. And we get 4/3. Which is much more simple than looking at the square root of 64 over 36. Now, using this, we can start to simplify some expressions, these rules here. Consider the square root of 18. So the square root of 18. You may ask, what is there to simplify? But because we're looking at a square root, we can always ask the question, is there a perfect square within this that we can take out of it? In 18, 18 is the same thing as 9 times 2. And I wrote it this way instead of course, 6 times 3. 18 is also 6 times 3. But I wrote it this way specifically because 9 is a perfect square. 9 is 3 times 3. So when I break up the square root over these two things, the square root of 9 is 3. And we leave the square root of 2 because the square root of 2 doesn't simplify any further. You can type it into a calculator and you'll get this long number that doesn't have any pattern to the decimal, and it's just not nice to work with as compared to the square root of 9, which is just 3. So we say 3 root 2 is the simplified version of the square root of 18. Now this was one way of finding the simplified version. You may not necessarily know that there is a perfect square within the number. In this case we did, right? It's 9. But you can always prime factorize this thing. 18 is, let's do it this way, let's do 3 times 6. And 6 is 3 times 2. Because the power on the radical, since this is there's no power written, it's understood to be 2. Because the power is 2, we're looking for groups of 2 because that's the power. And we have a group of 2 here. The 2 prime numbers is 3. And we have this 2 left over. What this means is we can put 1, 3, because we found one group. So we can put 1, 3 on the outside of the radical. So the square root of 18 equals 3. That one on the outside of the radical. And then the 2 is remaining is boxed in there. So that stays on the inside of the radical. Obviously the top way is faster. It's kind of more clean to look at. But the bottom way helps when you have really large numbers underneath the radical and you're not really sure what to do with it. The prime factorization method can help out immensely there. So this 3 root 2 is considered the more simplified version, and we'll see why in a second. But let's look at doing this operation, simplifying radicals, on a couple more examples. Let's look at the square root of 72 over 25. So first off, we can break up this radical over the top and bottom. And the bottom we see, that's just, whoops, thinking about the bottom number. The square root of 25 is 5. 5 times 5 is 25. Now the square root of 72 can be reduced. The question is, in what way? Well, you can ask, is there a perfect square in it? Or we can do the prime factorization method. Whichever way you want to do it, as long as you get the same answer both ways, and then you do it correctly. But I'm going to do it the prime factorization method. This one I think is a good problem to show that. 72 is 8 times 9. 9 is 3 times 3. 8 is 4 times 2. And 4 is 2 times 2. Now we have 2 times 2 times 2 times 3 times 3. These are all prime numbers, so I can stop. There's no more. This is the prime factorization of 72. Again, we're looking at a square root here, which means the power on the square root is 2. So we're looking for groups of 2. We have a group here, and we have a group here. I should say groups of 2, not as in like the number 2, but we're looking for pairs. That's what I mean by groups of 2. And then anything that does not have a pair is going to be boxed in here. So we found one group of 2 of the number 2. So we have a 2 on the outside. And we found one group of 2 of 3. So we have a 3 on the outside. So we get 2 times 3 times this boxed in 2 here. That stays on the inside because it didn't have a pair that goes with it. And of course the 5 is still in the denominator. And we can simplify that to 6 root 2 over 5. And that's simpler to look at than the original thing. You can, of course, also look at the square root of 72 and say, well, 9 is a perfect square. So we can rewrite this as 9 times 8. Gives us 3 root 8. And 8 has a perfect square within it, namely 4. 4 root 2. Which gives us 3 times 2 times root 2. 6 root 2. And we get the same answer on top as we did with the prime factorization method. Whichever way makes sense, do that way. But I encourage you to try out both ways because the more methods you know how to solve a problem, the faster, easier mathematics is going to be in general, the more connections you're going to make, It's going to help you in the long run. All right. What is the simplified form of the fourth root of 32? Now here we're not looking for perfect squares because the power on the radical is 4, not 2. So we actually need to look for perfect fourth powers, if that makes sense. In this case, the prime factorization method helps out immensely because now we're not looking for groups of 2, but groups of 4. Let me show you here. 32 is, let's do 4 times 8. 4 is 2 times 2. 8 is 4 times 2. And 4 is again 2 times 2. Because the power on the radical is 4, we're looking for a group or groups of 4 numbers that are the same. And we have a group here. There's 4 2's. And this 2 is left by itself. This means we can put a single 2 on the outside of the radical. That's because we found a single group of 4 numbers that were the same. So we have 2 on the outside, and then we have a 2 on the inside, and this is under the radical of 4. And this is the simplified version of the fourth root of 32. You could also say it this way. This is the other method. 32 does have a fourth power in it, namely 16. 16 is 2 to the fourth power. We have the fourth power over each. And the fourth power of 16 asks what times what times what times what equals 16. And those have to be all the same number. And that is 2 times 2 times 2 times 2. So we have 2 to the fourth power of 2. And of course we get the same answer either way we do it. I think the prime factorization method works better with higher powers rather than just the square root, because they're harder to work with. They're not as normal to work with. All right, let's look at another one. Let's look at negative, the cube root of negative 125, m to the 9th, b to the 18th, and c to the 24th. All right, we can break this thing up. Negative 125, m to the 9th, b to the 18th, and c to the 24th. Now let's look at the number first. The cube root of negative 125. This actually is a perfect cube. If you're not sure, you can test it with your calculator. But negative 5 times negative 5 times negative 5 is negative 125. We have the negative of negative 5. Just do negative 5 cubed, and you'll see we get negative 125. Okay, now the cube root of m to the 9. This is a little less clear. There are rules that can help us with this later, but let's just try and figure this out on our own. We're trying to ask what to the third power equals m to the 9? What goes on the inside here to give us m to the 9? Now, this is what we have. M cubed gives us m to the 9. That's because a power to a power, we multiply the powers, and 3 times 3 is 9. So the cube root of m to the 9 is m cubed. You can ask the same question for the b, b to the 18. What to the third power equals b to the 18? Well, b to the 6th power, because a power to a power, 6, we multiply the powers. 6 times 3 is 18. If we get b to the 6th. And the last one, what cubed equals c to the 24? This is going to be c to the 8th. C to the 8th. If you're not convinced, m cubed times m cubed times m cubed. This these are all like bases, so we add the exponents, we get m to the 9. That's what the same thing as m cubed cubed. Okay, we can simplify this a little bit. 5m cubed, b to the 6th, and c to the 8th. All right, what we did here, it may be a little bit confusing. There are better ways of doing it, which I'll show later on. I just wanted you to think of it in this fashion, rather than using the strategies we can do later on, because it's just an interesting, different way of thinking about this problem. Now that we've talked about simplifying radicals, we can talk about combining them as like terms. So for instance, let's look at the problem 5 root 2 plus 3 root 8. There's really nothing I like when you look at these two things right off the bat. However, if you first simplify the radicals, we will actually be able to see that we can do more with this expression. Now 5 root 2 can't be simplified, right? The square root of 2 is a prime number by itself. You can't break that down at all. There's no perfect square within it. So 5 root 2 is simplified already. However, the 3 root 8 can be simplified because the square root of 8, let me write it like this. 8 is the same thing as this 4 times 2. So we can break that up. We can just break this up into this portion here. The square root of 4 is 2. And 3 times 2 is 6. So now this becomes 5 root 2 plus 6 root 2. And let's say that I say x equals root 2. Then I can rewrite this thing as 5x plus 6x. And we know 5x plus 6x, these are like terms, right? They have the exact same variable. This gives us 11x. But since x equals root 2, we get 11 root 2. As long as the radical, here we have a square root, and here we have a square root. These were not common radicals, but these here, these radicals, I'll do it in a different color. The square root of 2 and the square root of 2, they have the exact same power on the radical, and they have the exact same radicand, the thing on the inside. As long as they're the exact same, then these are in fact like terms, and we can combine them. 4 root 3 minus 2 root 3. Well, both of these have the square root of 3, which is the exact same radical. So we're going to subtract the numbers in front. 4 minus 2 is 2 root 3. And there we go. Now, let's look at one that's a little more involved. 4 root 50 minus root 72 plus root 8. So these radicals are definitely not the same, and the first thing we want to do is we want to simplify them to see if they actually simplify to be the same thing. So let's look at root 50 first. You can use the prime factorization tree, or you can ask the question, is there a perfect square within 50? Because this is a square root, so we're looking at just perfect squares. And there is. 25 is in 50. So I can write it like this, because 25 times 2 is 50. And the square root of 25 is 5. Square root of 72, we've actually done this one already. It's going to become, let's see, I believe it's 16. No, not 16. It's 36. 36 times 2. The square root of 36 is 6 root 2. Okay. Then we have the square root of 8. Square root of 8 becomes 4 and 2. 4 is a perfect square. 4 times 2 is 8, right? And then the square root of 4 is 2, root 2. So 50 being 5 root 2, we have 4 times 5 root 2 minus 6 root 2 plus 2 root 2. Right? That's what these became. Became that one. 4 times 5 is 20. 6 root 2 plus 2 root 2. And these are in fact all like terms. They have the exact same power on the radical and they have the exact same radicand. So 20 minus 6 is 14 plus 2 is 16 root 2. And that is definitely much more simplified. Kind of the last bit here about radicals is that they are actually pretty much the same thing as exponents. In fact, we have a property for that. B to the, let's say the pth power of the pth root of b is the same thing as b to the 1 over p power of the exponent. And because they have a direct connection between exponents, that means radicals, if you write it in the exponential way, has the same properties of exponents as exponents. You can use the same rules, the product rule, quotient rule, all those things. And it can be sometimes easier to work with to work with the powers more than with the radicals. And sometimes it's easier to work with the radicals than the powers, whichever context dictates that you should use. I should say that b to the m over p, this is where we have some power in the numerator. This can be written two ways. This can be written as the pth root of b to the power of m. It can also be written as b to the m power the pth root. What's difference here is what happens first. Are we taking the mth power of b first, or are we taking the pth root of b first? Typically, I think with these types of problems, this one's going to be easier because when we take the pth root of b, the number gets smaller because we're asking like, what's the cube root of 8, right? The cube root of 8 is 2. So we went from 8 to 2, so we went to a smaller number. But context will dictate which way you should use it, which way is going to be the most beneficial. All right, let's look at some of these problems. The square root of 3x to the 5th times the square root of 15x squared. Now in this case, the powers are not going to work better because we don't have any kind of rules for that. We do have a rule, but it's a lot clearer to see here that we can actually combine these in one fashion. We can't simplify it down very much. It's actually going to be easier to simplify by combining them first. Here we have 3 times 15 is 45, and x to the 5th times x squared is 5 plus 2 is 7. Now we can simplify this. I think in a much easier way. 45 is 9 times 5. 9 is a perfect square. So we have 9 times root 5. And now I can show you the other method for solving the square root of x to the 7th. So for this, the square root of 9 is 3. We have 3 root 5. X to the 7th we can look at instead as to the 1/2 power here. This gives us x, a power to a power means you multiply the powers. 7 times 1/2 is 7/2. And we can kind of break this thing up into a mixed number. We can say 7/2 is the same thing as 3 and 1/2. Now this is really just saying x cubed times x to the 1/2, because 3 and 1/2 is just 3 plus 1/2. And when you have an addition of exponents, it's the same thing as multiplication of the bases. So what we can do is we can have 3x cubed on the outside, and x to the 1/2, well, that's just the same thing as the radical of square root of 2. That's the property I just showed you here. That 1 over p power is the same thing as the power in a radical form. I can rearrange this a little bit and combine the radicals to give us this. All right, this method here, it's not always quite clear to do that. There's probably a better way of doing it this way, by breaking down x to the 7th. X to the 7th is just going to be x to the 3 times x to the 4. X to the 3 is x squared times x. X to the 4 is x squared times x squared. I'm just making sure all the powers add up correctly. And you're always going to have this where in the end you're going to have 7 of these x's, because we started with a 7 power here, so we should have 7 of them. Now we're looking for groups of 2 because this is a square root. So here's a group of 2, here's a group of 2, there's a group of 2, and we have 1 left. So we have an x from that group, an x from that group, an x from that group. In other words, 3 x's, and this x remains on the inside. Let's look at another one. The cube root of s squared t to the 4th times the cube root s to the 4th t to the 6th. These are again 2 of the same radicals, so I can combine them underneath one thing. Times s to the 4th t to the 6th. And I can combine these. S squared times s to the 4th is s to the 6th. T to the 4th times t to the 6th is t to the 10th. I'm going to write this as a 1/3 power here. Now I can distribute this 1/3 to both of these and say we have s to the 6th. We have power to the power. I'll just write it out like this. 10 to the 1/3. And here we have a power to a power. So we're going to multiply the powers. 6 over 3 and t to the 10 over 3. And now you see 6 over 3 is just 2. And 10 over 3, that can be reduced in whichever way you want to. Sometimes the fractional power is fine. But I will reduce it. 3 can go to 10 3 times. So we have 3 can go to 10 3 times. 3 times evenly, with 1 left over. Let me show it like this. That's going to be t cubed times t to the 1/3. It's the same mixed number method I showed previously. It's just a little bit, I think it's a little bit cleaner actually, because 9/3 plus 1/3 is 10/3. And t to the 1/3 power, well, that's just the cube root of t. Okay. Last one, we'll do the square root of a times the 4th root of a cubed. Now this one's a little bit different. Here we have different powers of the radical. To do this, it's going to be better to work with the powers themselves rather than the radicals, because there's not very much we can do with the radicals. The first one is a square root because it's not written there. The next one is a 4th root. So a to the 1/2 times a to the 3/4, because we have a power to a power. And now to combine these two things, we need to have the same radical, which becomes the same denominator, really. So I'm going to multiply this first one by 2 over 2 in the power, and we get 2 over 4 times a to the 3 over 4. Now you can see that we actually have the same radical. It's a fourth root on both of them. We have like bases multiplying here, so we can add the exponents. And here we had to have the same denominator so that we can actually add these exponents. 2/4 plus 3/4 is 5/4. And this, you can see, we can break this up into a to the 4/4 times a to the 1/4, which gives us a fourth root of a. Because again, 1/4 power is the same thing as the fourth root, and 4 over 4, that's just the power of 1. So we just get a on the outside.